Okay, we're getting really close to talking about one of my favorite theorems, which is basically the classification of representations of p-adic GLN. Um, and well, there's different names by this. We're gonna specifically, I want to talk about the Zelevinsky classification, which uses this combinatorial tool called multi-segments. And it's really cool because it really gives this sort of nice combinatorial way to play around with these representations. So even though you might feel at first with some of these like crazy infinite dimensional representations, like you don't quite have your hands on it in the same way when you're playing with like certain, you know, representations of finite groups that you define very explicitly. These combinatorial gadgets give you such a cool way to organize these representations. And it really is part of something, we'll talk about eventually, which is the Langlands classification theorem, which gives a more general way of classifying that, of classifying the irreducible representations of p-adic groups. And one thing I'd like to do, which actually doesn't appear in the literature anywhere, even though it's like an elementary calculation, is showing that the Zelevinsky classification is a special case of the Langlands classification. And at first glance, some people might say, well, isn't it obvious? There's a little technical subtlety. Again, elementary mathematically speaking, but anyways, without further ado, let's jump in. So before we touch that, we need to modify our definition of induction slightly, right? So I talked about like induction from a subgroup of some, representation, and it's this space of functions where, like before, if the representation we're inducing is like v pi, uh, we have this factorization property. And we tossed in this condition that there existed some open subgroup so that our function was right invariant under that subgroup, right? So that gave us some sort of topological um, modification to our definition. There's one other thing, and well, a couple other things. So we want to upgrade this to parabolic induction. Parabolic induction. And we want to normalize it. Okay, so that's the topic of today's video. And then hopefully tomorrow we'll actually get started on the multi-segments. So let's talk about the parabolic first. We noticed last time that induction in the literal in the sense of this construction we've defined, but then it's a nice confluence of terminology because there's also induction in the sense that we literally take representations on smaller copies of GLN and build them up, right? We notice that I have like we have these like block diagonal copies of GLN of different sizes that all fit inside subgroups of our big GLN. And I mentioned that these are called Levy subgroups if you've seen some geometry of algebraic groups. And I guess I don't want to go into a total explanation of why this is, but Levy subgroups pair very nicely with something called parabolic subgroups. So why do we care about this? To just give you a brief explanation is that there's how do I say it simply? There's just clearly the Levy subgroups have this very nice structure. And from the perspective of algebraic geometry, which, okay, if you don't know that, like, don't worry, I'm not trying to scare people. We're not going to go too crazy. Eventually we will get into the thick of it. But the point is that, like, for a very general linear algebraic group. A subgroup is parabolic if the variety that you get is projective. Actually, I'm lying a little bit. It has to be a complete variety, whatever that is, but and then it's implied that it's projective, whatever. The point is, probably you've at least heard of projective varieties, and hopefully you're at least familiar with the idea that these are somehow nice, right? Like projective space, these are projective spaces are, of course, projective varieties, and these have like very nice properties, as do things like Grassmannians and whatnot. So, in fact, these are examples of what one might call a generalized flag manifold. So if you don't know what that is, not a huge deal. Again, we'll probably get into it in more detail. But the point of this is for GLN, we have a nice description. So there's all these fancy terms. I'm just trying to motivate like why we want to switch perspectives. And it's because, okay, these parabolics have nice structures. Other stuff we can say about root systems and whatnot. But to be very explicit, in the case of GLN, first, let me describe for you the standard parabolics. And technically, this depends on choice of Borel subgroup, but we're gonna just sort of for those who know what that even means, we're gonna pick the upper triangular matrices. So let's whatever. Not gonna worry about it. So let's describe whatever these standard parabolics are first. And in order to do that, so again, it's going to be in bijection with all the partitions of n. So I just take some, r different numbers that give me a partition of n. So this gives me a Levy subgroup of this form, right? So we can call that, I don't know, maybe L, n, n1 up to nr. And then the unipotent radical, so, that means something and has some general definition. Forget the more general definition for now, but the unipotent radical associated to this partition is now it's going to be everywhere up above where we had a copy of GLN. You're just going to plug in the Ni by Ni identity matrix. And then everywhere above these matrices, you can let these entries be anything. And so this will be an invertible matrix in GLN, QP, let's say. And then the parabolic subgroup attached to, maybe I'll call it n vector notation for short. So I'll write that as a shorthand for n1 up to nr. Is just going to be, I should define this is so U n vector is the group of all such matrices of this form. So the parabolic is going to just be the product within GLN. So this is the group generated by all things of the form LU, such that L is in here and U is in here. So by the way, this is actually a form of semi-direct product, right? Because, well, you have your L and N, and you have an L prime and an N prime, and you want to rewrite that as an L. Maybe I should use different letters. I don't know. L2, N2, right? And which way is the semi-direct product? I probably should have looked it up before, but I think it's this way. I always write this notation in the wrong direction, but not a big deal. You know, it doesn't even matter if you don't know what that means. I mean, this is literally it. This is it's the group, you know, the subgroup generated by all of these products, right? So everything in this group can be written in the form something in the corresponding levy times on the right something in the corresponding unipotent radical. So we have a very explicit form. And we're going to do something a little bit silly first. So parabolic induction, maybe seemingly silly, because remember, we want to take ourselves from representations of the Levy subgroup, because those are GLN for smaller copies of GLN, and get up to our larger GLN. But we're going to do this thing called inflation. So before we perform induction, we're going to extend our representation on the levy to a representation on the entire parabolic. So what I mean by this is our parabolic induction functor is going to be, so sometimes if I have a levy, sometimes you'll see in the lower script it'll be written with the parabolic you're inducing from. Sometimes I like to include the levy, although I guess that's implied in the choice of parabolic. So we have P up to well, I'll write GLN, or maybe just as a shorthand, we know that GLN is our G, so I'll write this. And so now it's going to be, you know, just like before, we'll have our functions, they're going to have their topological thing. But now, so if V pi is a representation, you know, smooth admissible representation of my Levy subgroup, the condition is now going to be F times, now, something, oh, maybe I'll erase to make space for the, oh no, this is fine. So this will be F. And now everything in my Levy subgroup, right, factors as L and U. So if I have something in the Levy or in the parabolic, it'll look like L times U. And so we basically just forget about this unipotent part. So we're still going to have our representation pi L acting on here, and this will be f of x. And actually, this is the thing I need to erase to make a little more room. So pi L f of x, right? For all L, U, X in their appropriate spaces. And, you know, topological things. There's one other thing that we need to do before we're fully set up. And that is we need to put in a little twist by a character. So let me just tell you what it is first, and then I'll explain why it's the case. So in particular, the Borel subgroup, this is, so remember, if I scroll up, you know, we've got our oh, I forgot to tell you. So those are the standard parabolics. There are other parabolic subgroups, but they're all conjugate to a standard. So I've defined for you, right? The standard parabolics are exactly the ones of this form. And then let's say, general parabolic is something of the form, anything that's of the form, which is a conjugate of that parabolic subgroup for some G and G, by the way. So again, there's, you know, fancier, more proper definitions. We'll get there. And our Borel subgroup is an example of a minimal parabolic. Minimal in what sense? Well, a number of compatible senses. But again, remember we have this bijection between our standards and partitions of n. So let's take the smallest partition of n, and that's when all of these n1s are 1, right? So the Borel subgroup is going to be just a bunch of GL1s down the diagonal, which is to say, I mean, GL1, this is, it's going to be a bunch of QP crosses down the diagonal. Which is great because remember this whole idea we hit on last time was like, we understand we understand characters of GLN now, and in particular, sort of like the simplest one is GL1, and let's try and induce those to get at these representations. So the Levy component is just going to be well, you might know this by another word, the torus, right? This is just the subgroup of all diagonal matrices. And the other thing, following the pattern I said before, is just you're going to put ones all down the diagonal, and then everything in the upper triangular matrices are going to be just any non-zero entries you want. So when you look at the set of all of these multiplied together, this ends up just being the group of upper triangular matrices. Cool. And so something I want to say here. Oh yeah, it's a little more complicated than I thought. That's okay. That's okay. We'll get there. The point is I'm going to define a character delta B on these elements of my Borel subgroup. So if I have something of the form, so let's call it well, L for the thing that's over here, and U and L, right? This is just going to be diagonally L1 down to Ln. I'm going to define a character delta of Lu. It's simply going to evaluate L1 with respect to my p-adic absolute value. And then it'll be n minus 1. And then I'm going to multiply that by L2 to the n minus 2 and ... all the way down until Ln is going to be evaluated, and that'll be at to the power of 1 minus n. Okay? So I claim that this is a character. I just need to check that it respects multiplication. And it's a very special character. We'll get into the details of like p-adic integration and measure theory and stuff eventually. For now, I'll just tell you, for those who happen to know, on our locally compact groups, we have like a God-given measure. Actually, that's only true up to scaling, right? It's called the Haar measure. So just some way to, measure the size of certain kinds of sets, and therefore, do stuff like solve integrals. And it's left invariant under translations by the group action, but it might not be right invariant. So let me say this. But there's also correspondingly, so you sort of get this God-given left invariant Haar measure. Oh yeah, I do want to say L for left, left measure, on our group G or something. And you also have one that's a right invariant measure. And you can actually translate between them by means of characters. This is called the modular quasi-character. And so if I've written things correctly, this is the way that you translate between those two measures. So it's this character. Normally it's defined by the character that interpolates between these two measures. So the point is this is coming from measure theory, but don't worry about that because this is exactly what it is for the Borel subgroup. We need to know what it is for all of the parabolics. The formula is a little bit messy. I'll write it out next time. I just forgot to prepare to write it down now. But it's something like this. You just group together these things in different ways and you have to adjust the exponents a little bit. And so the point of this character is if we go up to our induction, is I want to toss in delta of P. So for each of my parabolic groups, I'm going to have this character that interpolates between my Haar measures. And I want to take the square root of that character. And so that'll just be at L. Well, you could write LU, but, by definition, right? By the definition I've given you here, this is equal to delta B at L. And the point of this, so I mentioned below that this is related to like integrals and measure theory. And the point is, again, if you've done some other representation theory, you know that there's some special thing to be had about unitary representations. And basically, we put this choice of character in. I mean, all the theory would work the same if we didn't have this character here. We would just, our writing conventions would be slightly differently. But we put it in here because we want to make sure, just like how we have smooth admissible representations go to smooth admissible representations, we would like unitarity to be preserved as well, right? So if we're somehow like lifting up to find these representations, and that's something that this has to do. So it's really just some sort of choice of normalization. It's important we're on the same page about fixing our convention, but it's also in some sense immaterial. Okay, so we're done with defining the parabolic induction functor. There's one last thing I want to mention to you before I go, and that is the fact that, so again, if you know about Frobenius reciprocity, right, you can just, it's this homomorphism, it's this bijection of sets of homomorphisms, or if you like, it's a natural transformation of functors. You might ask, well, we've gone and we've changed this thing that we have induction, and we used to have this nice thing called restriction that was adjoint to our, or had this, if you don't speak functors, had this bijective property with the induction functor. Is there still something like that for parabolic induction? By the way, I want to note this does technically depend on the choice of parabolic, right? So keep that in mind. It's going to be important. And it turns out, yes. So there's something called the Jacquet functor. And what that's going to do is, so we have, say, rep L, our Levy subgroup of GLN, and we have our parabolic induction going up to our smooth admissible representations. Jacquet, in the same way, is going to, sometimes I've seen it written like this, but maybe I would just write it J sub P. It's going to go in the opposite direction. So it's going to be our adjoint. What I mean by that is there's a bijection. So this will be homomorphisms. I have, let me set this up. So pi v lives over here. W rho lives over here, and abusively I'll just refer to these representations by the homomorphism. So it'll be the case that the homomorphisms from the Jacquet of rho into pi will be in bijective correspondence with the homomorphisms from rho into, running out of room here, the normalized parabolic induction of pi. And moreover, these are somehow compatible. It's a natural equivalence. So again, this is really a statement about an isomorphism of functors. So that's what I mean by naturality. There's some compatibility of maps here, if you happen to know what that means. One last thing, before I define this, by the way, it turns out that there's an adjunction on the other end as well. So there's this says, in the fancy language, again, if you don't know adjunctions, just think about it as Frobenius reciprocity. I also always draw this thing the wrong way. The statement I've written above here has the Jacquet functor on the left and the induction on the right. There's also a version where this goes on the Jacquet functor goes into the right slot. And a form of induction, well, it is basically induction. It's just, remember I mentioned the choice of parabolic matters. There's a special parabolic that is sort of the most different from the parabolic you started with in a certain sense, and that's called the opposite parabolic. And so it turns out we actually have adjunctions on both sides. So this means that both of these functors are exact. Okay, I'm worried I've maybe scared away non-categorical people because I said we're going to have a very down-to-earth description of these representations. And we will. You don't really need to know about these categorical facts. They are useful. I just wanted to, I can't help myself but mention them. So hopefully I didn't lose you on that. Let me just give you the very explicit definition of the Jacquet functor, and maybe that'll bring us down to earth and allow us to wrap up this video. So suppose I have my representation, my smooth admissible representation of GLN, QP, right? That's what I mean when I write G, at least at this point in the series. And I'm going to define the space V. So I'm going to suppose that I have a parabolic, which factors as LU. I'm going to define the space VU is going to be the span, the complex span of everything of the form pi G V minus V, where G runs over all of G, and V runs over the entire vector space. And what I'm going to do is consider the subspace of my original vector space, V modded out by the subspace. Now, why? Let's think about this. When I defined the normalized parabolic induction, right, we did this thing called inflation, right? We sort of artificially, it's like we artificially, like another way I could have written this is I could have defined, pi sub p to be extended to a representation to all of my parabolic, but just by defining it to act on the first factor L, right? And then I could have written this first part like this, that it factors as FP. I have my character, and then pi P of P. There should be big P down here, F of X. right? So it's just like I artificially like inflated my representation of the levy to a representation of the entire parabolic. And so if I want something to go in the other way of induction and have this nice property with it, since I sort of artificially added on this action of the unipotent radical, then probably if I have this functor, this operation going the opposite direction, I should want to kill off that thing that I artificially inflated, right? If I want to get back some sort of semblance or similarity with the things that I started with, right? So that's why we're modding out by this subspace. And then we're going to define so how does the Jacquet functor of my, the Jacquet representation of my original representation act for a given G in my levy component, because remember, I want this thing to live in smooth admissible representations of L. I want this to take a vector, which is now a coset. And what I'm going to have it do is, of course, act by my representation, right? It's just like, you know, this is analogous to restriction. So it's just going to act on that representative of the coset. And you can show that this is going to be a well-defined, this will, in fact, give you a well-defined representation. But now, remember, the other thing I did with normalized parabolic induction is I gave this little twist. Where did I put induction now? I gave this twist as well, right? So we like inflated to the full parabolic, and I put in this normalizing factor. So probably it should make sense to you, and specifically the normalizing factor is multiplying by this character to the positive 1/2. So what I should do then is I should multiply by that same character, but to the minus 1/2. Okay, so minus 1/2 times my G. And so this gives you a well-defined representation. And so now we have two ways of going up from here and down from here. Now, I could have gone right to the classification just talking about this thing, but this really is an important part of the story. And I think I'll talk about that in the next video. So I'm going to leave it here for today. Let me know if you have any questions, as always. And hopefully I'll see you all soon.